Hello. Now, last class I have discussed about the footing which is loaded eccentrically. I have discussed about the one-way eccentricity and two-way eccentricity. Now, in this class I will discuss the how to calculate the bearing capacity of the soil in layer condition. Now, as we know that soil is not a homogeneous soil, because but till now the most of the things that I have discussed is to calculate the bearing capacity of homogeneous soil. Now, soil is a layered type of material. So, now the properties of the soil according to depth is not same, it is changing. Now, if the soil is the condition is the layered condition, then how to calculate the bearing capacity of this layered soil, that I will discuss in this class. Now, suppose if we go for the bearing capacity of a layered soil system, now we will discuss the bearing capacity of layered soil. Now, the derivations or the expression which is available for this to calculate the bearing capacity of the soil, which is basically for the homogeneous soil. Now, if the soil is in this form, that this is the ground surface, here we are applying this footing, this is a ground surface and this is width of the footing, and this is the depth of the footing df. Now, this is we are considering the two soil layer. This is one layer which is the strong soil, which is strongest soil, or layer 1, and layer 2 which is weaker soil. So, this is the strongest soil and this is the weaker soil. Then how to calculate the bearing capacity of this soil condition, and suppose the this is the properties gamma 1 C 1 and phi 1 for the layer 1 and gamma 2 C 2 and phi 2 for layer 2. Now, if the stronger soil, this is the interface, if the stronger soil, and one thing that the depth of the stronger soil from this base of the foundation is h. See, this is the up to this the up to the h depth from the base of the foundation is the stronger soil, then the weaker soil. Now, if the depth h is relatively small, then what will happen? Then there will be a punching type of shear failure for this stronger soil layer, and then general shear failure for the weaker soil. So, suppose this is the punching type of failure surface, punching shear failure type of failure surface for this strong soil, and then this is the general failure surface which is expected for the weaker soil. So, this type of failure surface that will develop. So, now if I draw one line, vertical line. So, what are the forces which is acting? Suppose in this, because here it is the general shear type of failure. So, that means we can calculate this is the Q bottom or the bottom layer, and for this punching shear failure, what are the forces that is acting? So, first is the adhesion C A. is which is acting two sides of this layer, because suppose this is the one block which is falling, or that means this is the size. Now, another thing, the passive resistance, the surrounding soil that will provide for this zone or this zone, that is the passive resistance P P, which is acting at angle of delta. Similarly, this side also, this is the P P, which is acting as an angle delta. So, these two types of force which are all acting here, suppose this is the center line. So, one is the adhesion in the both sides of this layer, and passive resistance coming from the soil of this side and soil from this side, which is acting as the angle of delta to the perpendicular of this line. This is P P. P P is the passive resistance. Another thing, that if this H value here, if this H, which is the distance which is depth of this layer or from the base of the footing, is relatively small, then we will get this type of failure surface. Now, if the distance is relatively large, then we will get the most of the failure surface will be in the stronger layer. So, the failure surface or the effect of the loading intensity or the footing load will not act. Suppose this is the footing load, that is Q ultimate. So, that effect will not go to the second layer or the weaker soil layer. So, most of the failure surface or will be located at the stronger layer. In that case, the general expression for the shear failure expression, general shear failure expression for the or for homogeneous soil or single layer soil, that we can use to determine the loading of our bearing capacity of the soil. Now, if it is relatively small, then we will go for this approach. Now, one thing is that this value. So, if I go for the different loading condition, so what will be the different loading condition for this case? So, first we will calculate the Q u for the loading condition, the vertical load Q u, which is acting in the downward directions, that is equal to the perpendicular load that is acting. So, the resistance, that Q u is the total load bearing capacity. This is the some portion of the resistance that we will get from the bottom layer and some portion we will get from the top layer. So, this is the summation of the resistance or the load which is carrying by some portion by the strong layer and some portion by the weak layer or the bottom layer and the top layer. Suppose in the bottom layer it is as usual the general shear failure. So, we can write this is the resistance, that is Q bottom. So, Q bottom is the load carrying capacity of this bottom layer or the resistance that is coming from this bottom layer, plus the resistance that is giving by this top layer, that will be 2 into C A, that is the addition. 2 means one from this side, another from this side, plus because here P P is acting as a delta. So, the sign component that will act in the upward direction. So, that will give the upward resistance. So, that is P P into sin delta. So, that means these are the upward forces divided by B, because these things are acting as a width of B, minus gamma 1 into H, because this is the this load or the Q that is acting here, gamma 1 into H, that is the surcharge below the base of the foundation up to the second layer or up to the starting of the second layer or up to the end of the first layer. So, that is the total force, that means the contribution of the Q is the contribution from the bottom soil plus the contribution from the top layer and minus this value surcharge that we are deducting, because this surcharge we will not consider as a contribution, because it was existing previously. So, now this are the total load. Now, here P p we can write, that is passive force per unit area. So, that is the passive force per unit length. Here we can write that C A is equal to small c a into H, because C A is the total load, that is total resistance due to addition, and small c h is the addition which is per meter. So, that is the total, and then as it is acting as this length h, so this will be C A into H. So, if we put this value in this final expression, then the form of this expression will be, because our original expression is Q u is equal to Q b, that is the bottom resistance, into 2 into C A plus P p into sin delta divided by B minus gamma 1 into H. Now, here C A is basically small c a into H. Now, if we put the small c a in this expression, then Q u, that will be Q b plus 2 small c a into H divided by B plus, now we can write P p on the other terms in the final form is gamma 1 H square 1 plus 2 d f B K p h into tan delta divided by B into gamma 1 into H. Now, these expressions again we are taking from this book by B. M. Das. This is Das B. M. 1999. So, this is the final form of this expression that we are using, where K p h horizontal components of passive earth pressure coefficient. So, this is the final expression that we are getting to calculate the ultimate load carrying capacity of this layer soil. K p h is the horizontal component of the passive earth pressure coefficient. Now, let that K p h tan delta, that is equal to K s into tan phi 1, where K s is equal to punching shear failure or coefficient. So, as I have mentioned that for the first layer it will be punching shear type of failure. So, this is the punching shear coefficient. Now, if we put this kph tan delta is equal to ks tan phi, then the QU expression will be QB plus 2 CAH B plus gamma 1 H square 1 plus 2 DF into H into Ks tan phi 1 by B minus gamma 1 into H. Now, in this form we will get this. So, here this expression, this is also df by H. So, this is 2 df by H and this is also 2 df by H, and then we just replace this kph tan delta by ks tan phi 1. Now, here now Ks, this punching shear coefficient, is a function of two things. One is Q2 by Q1 value, another is phi 1. Now, here it is mentioned that phi 1 is the friction coefficient or friction angle of the first layer, and Q2 and the Q1, where Q2 or Q1 is the C1 in C1 for the first layer plus half gamma 1 B in gamma 1, and Q2 will be C2 in C2 plus half gamma 2 B in gamma 2. So, here we can see that the one second component, that is due to the surcharge, which is not present here. So, that means the Q1 and the Q2 are the bearing capacity if the load footing is placed at the surface. So, that means this is for the surface loading conditions where Q is 0. So, second term, that is also 0. So, that is if we for the same material properties, this Q1 is the bearing capacity for the first layer for the surface loading, and this is Q2 is the bearing capacity of the second layer for the again for the surface loading. Here we are not applying any correction factor, this is in the general form. So, that will be Q1 and Q2 that we will get by this thing. So, this Ks is a function of Q2 by Q1 and phi 1. So, if we know this Q2 by Q1 and phi 1, then we can calculate Ks. Now, another thing that this is applicable if h is relatively small. Now, these expressions we can use in different form. Then, if h is relatively large, as I have mentioned that if h is relatively large, then all the failure surface will be on the first layer itself. So, that means our QU will get, that is equal to QT, where QT is the bearing capacity of the top layer. So, that means we will get C1 NC1 plus Q NQ1 plus half gamma 1 B in gamma 1. So, by using these expressions we can calculate the bearing capacity, ultimate bearing capacity of the top layer, because if h is relatively large. So, now we can conclude that if, because the bearing capacity as the first layer or the top layer is stronger layer and the second layer is weaker layer. So, bearing capacity of the combined contribution coming from the combined of first layer and the second layer, that cannot be greater than the contribution or the bearing capacity of the top layer itself, because the second layer is the weaker layer. So, bearing capacity of this first layer is Qt, and if the all the failure surfaces are located in the top layer, then that is the maximum load carrying capacity, that is Qt, because the first layer, the top layer is the stronger layer and second layer or bottom layer is the weaker layer. Now, if the H is relatively large, then this Qt will give you the load carrying capacity of the soil, and that is the maximum. Now, if H is relatively small, then the contribution of the first layer that will reduce, and the contribution of the second layer that will introduce in this ultimate load carrying capacity, and that part will increase, and the contribution of the second layer that cannot be greater than the contribution of the first layer, as the second layer is weaker layer. So, if I get the combined bearing capacity, that is contribution from the first layer and the second layer, that should not be greater than the contribution of the first layer itself. The contribution, I am telling that, if H is relatively high, that all the contribution, all the bearing capacity is due to the resistance of the top layer. Now, if H is relatively small, then the bearing capacity, ultimate bearing capacity that you will get, that is the some part is coming from the resistance of the top layer and some part is resistance from the bottom layer. Now, summation of these two, the some part of the top layer and some part of the bottom layer, that cannot be greater than the total contribution or the contribution coming from the top layer itself. So, in that conclusion we can write that Qu is equal to that Qb bottom layer plus, that is the contribution from the bottom layer, plus 2 CAH B plus gamma 1 H square 1 plus 2 dF by H into Ks tan phi 1 divided by B minus gamma 1 H, that cannot be greater than Qt. So, this is always less than, that can be equal. So, this is less than equal to Qt. So, in this now further it is given that for the rectangular footing, foundation, we can write that Qu is the contribution from the Qb plus 1 plus B by L, it is introduced for the rectangular footing, into 2 CAH divided by B plus gamma 1 H square 1 plus B by L into 1 plus 2 dF into H into Ks tan phi 1 by B minus gamma 1 H, that cannot be greater than Qt. So, this is for the rectangular footing. Now, again we can calculate the what is the value of Qb and the Qt, where Qb is the ultimate load carrying capacity of this bottom layer. So, this will be C2 NC2 into SC2, SC2 is the shape factor, plus gamma 1 dF plus H, that is the surcharge which is coming from the top layer, into NQ2 and SQ2. then plus half gamma 2 B n gamma 2 into S gamma 2. So, this n C 2 n q 2 and n gamma 2, these are the bearing capacity factor, and SC2, SQ2 and S gamma 2, these are the correction factor for shapes or shape factor. Now, similarly, QT for the top footing, that will be C1, NC1, SC1 plus gamma 1 here DF, this is the surcharge, into NQ 1 SQ 1 plus half gamma 1 B n gamma 1 into S gamma 1. So, here SC 1 or 2, SQ 1 or 2, S gamma 1 or 2 are shape factor. So, this way we can determine the QB for the bottom layer loading ultimate load carrying capacity, Q2 is the ultimate load carrying capacity of the top layer, which is we are including the shape factors also. Here this dF plus H is the surcharge for the bottom layer, and dF into gamma 1 is the surcharge for the top layer, and dF plus H into gamma 1 is the surcharge for the bottom layer. Now, the next thing we will discuss a few special cases that or the different conditions, then how to get the different conditions. The special cases, that is first case this condition is the top layer is strong sand, that means this is purely sandy soil, whose that means C1 is equal to 0, and as the top layer is a strong layer. So, this will be strong sand, and the bottom layer is saturated soft clay, that means phi 2 is 0. So, this is the weaker soil. So, that means for the top layer C1 is 0 and for the bottom layer phi 2 is equal to 0. So, now if I calculate the QB with the shape factors, then we can write 1 plus 0.2 B by L, that is for the shape factor, and as for the bottom layer phi 2 is equal to 0. So, this is the then the C, that means the C 2 and the N C will be 5.14 and this is C 2. So, this is basically C 2, N C 2 and S C 2. S C 2 is 1 plus 0.2 B by L, C 2 is the cohesion of the second layer or the bottom layer, and N C will be 5.14 if, because we know that N C 2 is equal to 5.14 if phi 2 is equal to 0, that we know. And again that N Q, that part is also 1 and N gamma part will vanish if phi is equal to 0, that we know, because this is the common things for the all the cases. So, now we will get only the surcharge at gamma 1 into dF plus H, it is the bottom layer, and similarly the top layer, that will give you that this is the C1 is 0 top layer. So, first part is C1 is 0. So, first part C1, NC1 and SC1 that is 0. So, in second part we can write this is gamma 1 df into NQ1 and SQ1 plus half into gamma 1 B n gamma 1 into S gamma 1. So, in this fashion we can determine the QT and the QB. Now, as for the Q2 and the Q1, Q2 is basically here corresponding to the second layer or the bottom layer, and it is in the surface. So, if it is in the surface, then this surcharge part that is also 0. So, Q2 we can write that Q21 is 1 plus 0.2 into B by L, that is divided by half into gamma 1 B n gamma 1 into S gamma 1. And we can because this part this and again this 5.14 into C2, because the surface part as it is a surface footing. So, this part will be 0 and this part will be also be 0. So, only this. So, here the surface part if we neglect. So, this one will be 5.14 C2 divided by half into gamma 1 into B into n gamma 1. So, here we will get the Q2 and Q1. Now, how to use this Q2 and the Q1, that we will explain by using the, because charts are available to determine this Q2 with the help of this Q2 and Q1, and I will discuss these things after we complete the different cases. Now, next one, that means here for the first case QU will be 1 plus 0.2 B by L 5.14 C2 plus gamma 1 H square 1 plus B by L 1 plus 2 df by H into Ks tan phi 1 divided by B plus, because here gamma 1 df plus gamma 1 H is there, but in the original expressions also this QU, this minus gamma 1 H is there. So, minus gamma 1 H and plus gamma 1 H, these are cancelled. So, only gamma 1 and df that is present. So, only gamma 1 and df that should be less than equal to the QT, where QT value is gamma 1 df NQ1 SQ1 plus half gamma 1 B n gamma 1 S gamma 1. So, this will give us the ultimate load carrying capacity of the soil for this condition. Now, the next case or the case 2, that if top layer is stronger sand, that means C1 is equal to 0 and bottom layer is weaker sand. and here C2 again is 0. In first case the C1 was 0 and phi 2 was 0. In the second case C1 is equal to 0 and C2 is also equal to 0. So, here the QB that will be equal to gamma 1 because C1 and C2 both at 0. So, first term will be 0 for the both the cases gamma QB and QT. So, gamma 1 df plus H into NQ2 SQ2 plus half gamma 2B N gamma 2 and S gamma 2. Similarly, QT will be gamma 1 into df into NQ1 SQ1 plus half gamma 1 B N gamma 1 S gamma 1. So, similarly, Q 2 by Q 1 here we can write, but because in the surface putting. So, this part is 0 because surface putting, so both the cases it is surface putting. So, second part is it is not that because this is here df is 0, but this is top case it is 0, but here also df and h both are 0. That means, for the bottom layer also it is placed at the surface considering that there is no surcharge basically. So, this is 0, this part is 0. So, Q2 by Q2 by Q1 will be half gamma 2 B in gamma 2 is gamma 2 divided by half gamma 1 B in gamma 1 and S gamma 1. So, this B in gamma S gamma, the shape factor we are considering this is same. So, ultimately this will be gamma 2 into N gamma 2 and gamma 1 into N gamma 1. So, now how to calculate the ultimate load carrying capacity, that is QU, that means QB is gamma 1 df plus H N gamma 2 NQ2 SQ2 plus half gamma 2 B N gamma 2 S gamma 2. Again, where SQ S gamma, these are the shape factors, plus because this here the C is 0. So, this ultimate the general expression the C term is also 0. So, that part is gone. So, gamma 1 A square into 1 plus B by L 1 plus 2 df divided by H into K s tan phi 1 divided by B minus gamma 1 H, that is less than Q t, where Q t expression is given by this formula. So, that means you will get, so that would not be get. So, we have to check first, we calculate the Q u and then we will check by using this Q t whether Q u is less than equal to Q t or not. So, this should be less than equal to Q t. If it is not, then we have to use this Q t as our ultimate bearing capacity of the footing under this layered soil condition. Now, the third case, that is the case 3. In the third case, the condition is the top layer is stronger saturated clay. that means phi 1 is 0 and the bottom layer is weaker saturated clay, that means phi 2 is also 0. So, in the case 3 phi 1 is 0 and phi 2 is 0, then that means Q B and Q T. So, we have to calculate Q B and Q T both. So, Q B as this phi 1 phi 2 is 0. So, this part 1 plus 0.2 B by L into 5.14 C 2 plus gamma 1 into D F plus H. Sorry, this is H. So, gamma 1 D F plus H, because this term this in gamma 2 that will be 1, and as phi 2 is 0, that in Q 2 is 1 and in gamma 2 is 0, and here in C 2 is 5.14. Similarly, Q top, it will be 1 plus 0.2 B by L, this is 5.14. Similarly, this is plus gamma 1 into D F. So, ultimately we can write that Q 2 by Q 1, that ratio where it is in the surface. So, if it is in the surface, then this part is gone. So, this part is 0 again. So, that means this will be 1 plus 0.2 B by L 5.14 C 2, sorry, this one will be C 1, C 2 divided by 1 plus 0.2 B by L 5.14 C 1. So, that means the ratio will be C 2 by C 1. So, now the ultimately the Q u, that will be the Q b expression is 1 plus 0.2 B by L to 5.14 C 2. Again this gamma 1 D F plus gamma 1 H is present and 1 is minus gamma 1 H. So, both are cancelled, so only gamma 1 into D F will be present. So, now plus 1 plus B by L 2 C A H by B plus gamma 1 D F, that is equal to less than Q T, because as this phi 1 is also 0. So, that general term that tan phi 1 will be 0. So, that part is gone. So, only this part will be present. So, this we can write in this form for the rectangular footing. Now, the question is how we will calculate this. Suppose for this case 4, we know that Q 2 by Q 1 is equal to C 2 by C 1. Then how will use this charts and how will use this is Q 2 or this is Q 2 by Q 1. So, that is C 2 by C 1. Now, if we go for this chart, that this is the chart which is presented by Meyerhoff and Honda 1978, which is also the source is this book. Now, here this is, as I have mentioned, that this punching shear coefficient K s is function of Q 2 by Q 1 and phi 1. So, punching shear coefficient is a function of Q 2 by Q 1 and phi 1. So, if we know the phi 1 value, this is the top layer frictional coefficient, and if we know the Q2 by Q1, that is equal to, so these are the different value 1, 0.4, 0.2 and 0. So, by if we know this phi and corresponding different Q2 by Q1, we can determine the case. Now, this Q2 by Q1 in the different cases, this case 1, case 2, case 3, I have explained how to determine this Q1 and Q2 value, this ratio. So, first we have to calculate this Q2, because in the final expression this case term is present. So, that means in the case we have to determine. So, to determine the case value, we should know how to calculate this case. So, first step is, because we know this gamma 1, C 1, phi 1, this is the properties of the top layer, and then the gamma 2, C 2 and the phi 2, these are the properties of the second layer. So, these parameters are known to us. So, with the help of these two parameters or these things, first we will calculate the for the shape factors for different, because the dimension of the protein, that is also known to us. So, that means with the help if it is not known, then by trial and error method we have to determine these things, that how to use the trial and error method for any design of this foundation, that part I will explain when you will study the design of this foundation part. And then once we get this dimension, so suppose here we assume these dimensions are known. So, once we get the dimension, we can calculate this with the help of phi value, we can calculate bearing capacity factors for top layer and the bottom layer. Then with the help of dimensions, we can determine the shape factors for the top layer and the bottom layer. So, if these things are known to us, then we can determine what is the ratio of Q1 and Q2. So, once we determine the value of Q1 by Q2, this ratio, and then we know the phi 1 value, that is the top layer, then we can, by using this table or this chart Q1 corresponding to phi 1, we can determine. So, suppose this is Q1 by Q2 is 0.4 and theta is 35 degree. So, that means the case value will be 5. So, that means here this case value will be required to calculate the ultimate load carrying capacity of this layered soil. So, that case term is there as in the, as you have seen then in this final expression. So, there we will use the case. So, that is for the, if this phi 1, so top layer if it is stronger sand, because it is we are getting the case for the phi 1. Now, if the top layer is cohesive soil, the last case, because the top layer is stronger saturated clay, where the phi 1 is 0, then how to calculate these properties? Because here the phi 1 is 0, then you have to use this chart, because in that case we should know the Ca value, because this Ca value, but for the, if the top layer is a stronger sand, then this Ca part or the cohesion part, that is 0, because we are talking about the purely cohesive soil or cohesionless soil. So, if that is stronger sand, then Q phi 1 is present, but C1 is 0. Now, so that means that if the cohesion or the addition is 0, then we have to use for the stronger sand is K's value. So, by using the first chart, if with both the cases we have to determine this Q2 by Q1. So, once you determine the Q2 by E1, if the top layer is stronger sand, then we should know the value of K's. So, in the stronger sand we can calculate Q2 by Q1 and we know phi 1 value. So, by using the first chart or first graph, we will get the K's value. Now, in the second case, if the top layer is stronger saturated clay, then K's term is not required, but Ca term or adhesion term, that is required, because here we know that C1 value, but phi 1 is 0. So, once we get the C1 value, and here also we can calculate, because in the third case we have seen that Q2 by Q1 is equal to C2 by C1. So, now if we know the C1 and C2 value, so we can calculate the C1 and C2 value ratio. Once we get that the C1 by C2 value, that ratio, that is equal to the ratio Q2 by Q1. So, that Q2 by Q1 is C2 by C1. So, this C2 by C1 is known, because Q2 by Q1 is C2 by C1. So, once we get the C2 by C1, we will get the Q2 by Q1. So, and now using this chart, for this case also we can determine Q2 by Q1. Then by this, using this chart, then we know the C1 value. So, only unknown is CA. So, suppose for the Q1 by Q2 is 0.4. So, CA by C1 is 0.9. So, that means CA will be 0.9 into C1, but here C1 is also known. So, in this way we can determine the value of different parameters. So, once we get the CA, then in the final expression that CA term is required. So, we will get the put the CA value there, and we will calculate the ultimate load carrying capacity of the soil, because all the other terms, the thickness, dimension or the properties, those are known. Only main unknowns are Ks and Ca. So, those two things we can determine by using this chart. So, by in different cases we can we have to judge whether where we will use the first chart and where we use the second chart. If it is stronger sand in the top layer, then we will use the first chart, because we need to find the Ks value. If it is stronger clay, then we have to need to determine the Ca value, then we will use the second chart. But both the cases we have to determine Q2 by Q1, and I have explained how to determine this Q2 by Q1 in different cases. So, in this fashion we can, and in this way we can determine the ultimate bearing capacity of the layered soil. In the next class, I will discuss how to determine the ultimate load carrying capacity of foundation in slope, and then we will go for the analysis, or the, because most of the up to this, the most of the bearing capacity calculation we have done for the isolated footing, or next one we will go for the raft foundation, then how to determine the load carrying capacity of the raft foundation. Then we will go for the settlement calculation, because we are always talking about the bearing capacity. Then the next criteria, design criteria, settlement. So, those things we will discuss in the next classes. Thank you.